problem 889, construct a binary tree from preorder and postorder traversal. We are given two integer arrays, preorder and postorder. So where preorder is the preorder traversal of the binary tree of distinct values, and this distinct values is really important for such kind of creating binary tree problem. Otherwise, we cannot solve it. And also for the postorder array is the postorder traversal of the same tree. So we're going to reconstruct and return the binary tree. So we're going to use the two arrays basically, preorder array and postorder array, to create a binary tree. So if there exists multiple answers, we can return any one of them. So the preorder array is just the preorder traversal of the binary tree, and the postorder array is just the postorder traversal of the binary tree. Let's just use an example. For example, this node 1, it's going to be the root node, and then we're going to go to the left part, like 2, 4, 5, and then we're going to go to the right part. So we're going to go to the left part 2, 4, 5, and the right part 3, 6, and 7. And for the postorder traversal, we're going to first go to the left side, it's going to be 4, 5, 2, and then we're going to go to the right part, it's going to be 6, 7, and 3, and then we're going to go to the root. Let me just copy the two arrays to explain what kind of method we're going to use to solve such kind of problem. Definitely, this is not an easy problem. It's not like other traversals we can easily to recognize from where we can split the array, but for this problem, it's a little bit difficult. So for example, the obvious way is that what about we find the root node? So inside the preorder traversal, inside the preorder array, we can find the root node, which is going to be this value 1. Yeah, it's going to be this value. And of course, we can use this value to find where it is inside the postorder array. But it is not helpful for us to solve the problem, because even we know the root node, we don't know which part is from the left side and which part is from the right side. For our problem, if we want to solve it, basically it is a divide and conquer idea. We need to divide it and then conquer it. First of all, we're going to divide the left part and the right part of the subtree, and then we're going to conquer it. We're going to connect them together. But currently, we cannot divide it. So if we cannot use the root node, root value, I mean the first value inside the preorder traversal, maybe we're going to find we need to find another value. So actually, this value is going to be the second value. It's going to be this node 2. So because for this node 2, it's going to be the root node for the preorder traversal of the left subtree. As you can see, this node 2 is the left subtree for the preorder traversal for this node 2. And if we can find this value 2 inside the postorder array, so for example, this is a 2, and we're going to split it from here. Yeah, because for the postorder traversal, for this subtree, it will go to left, right, and the root node. So this root node is a splitting point. So we're going to use this kind of a property to solve the problem. So if we can find this 2 from the index, it's going to be index I, it's going to be here. So we're going to use index I plus 1 as the left part size. So 4, 5, 2 going to be the left part size. And similarly from here, we already know the left part size. The left size is going to be 3. And from 1, so we're going to code 3 node, it's going to be 2, 4, 5. So it means 2, 4, 5, this is going to be the left part. And after that, 3, 6, and 7, this is going to be the right part for the preorder array. And for the postorder array, we can just directly use 6, 7, and 3. It's going to be the right part, because this node 1 is going to be the root node. So in this way, we can split it into 2 parts, and we can recursively solve the problem. Now let's go to the coding to solve it. So I'm going to define a DFS. So inside it's going to be the preorder and postorder as always. So I need to check if not preorder. If the preorder is empty, I need to return a none. As I need to find the second value instead of the first value inside the preorder array, because inside the first value for the preorder array is going to be the root node, but I want to find the next node. It means the root node for the left subtree. So I'm going to find this value 2. Yeah. So before I find this value, the next value 2, I need to check the length of the preorder array. So if the length of the preorder array equal to 1, it means there's only one node inside the preorder array, so I can return it directly. It's going to be the tree node with preorder 0. Otherwise, so the length of the preorder array is going to be at least 2. So if it is at least 2, so I can use the property to check the left size. So the left size, I'm going to use the post order array to check. So the post order array, I'm going to check the index. So it's going to be the pre-order array with index 1. So in this way, we can find the left part. It's going to be 4, 5, and 2. Because we need to get 4, 5, and 2. For the index, it's going to be the index 2. But we need to calculate the size. It means it's going to need 2 plus a 1. Now the left size is going to be 3. Now we're going to use the left size to calculate the left and the right part. So I'm going to prepare a left and a right to calculate. I'm going to recursively calculate the left part and the right part. So the left part, the left going to be the DFS with the pre-order. So I'm going to start from the second value. It's going to be from 1 to the left size. I need 2 plus a 1. Yeah, because the left size is 3, so because I'm starting from 1, so I need 2 plus a 1 for the pre-order. So for example, it is from 2, 4, and 5. And the post order going to be, for the post order, I don't need 2 plus 1, so I'm gonna starting from 0 to left size. And similarly, I can calculate the right part. So it's going to be the DFS of pre-order from the left size plus 1 to the right part. And for the post order, it's going to be starting from the left size to minus 1, because I don't need to take the last value for the post order array, because that is going to be the root node. And here, the left size index is going to be the root node. That is why I jumped it. So for example, this is 1, 2. I'm sorry, the first node is going to be the root node. So I'm going to starting from 1 to left size plus 1, and then left size plus 1 to the right part. So finally, we need to return a tree node. I think this kind of writing is easier. Or you can just prepare a root node. Prepare a node or a root node, and you're gonna return the root. It's the same idea, but we can save a little bit, a few lines if we use this kind of idea. So the tree node gonna be the pre-order with the 0. This gonna be the root node, and then we're gonna put the left and the right part inside. Yeah, because for the left and the right, it just means this node dot left is gonna be the DFS. Yeah, we're gonna recursively call the DFS. If there's nothing inside the pre-order array, we're gonna give a none. For example, for the leaves 4, 5, 6, and 7, we're gonna give a none. We're gonna return a none. Finally, we need to call the DFS. So inside it's gonna be the pre-order and the post-order array. Now let me just run it. As you can see, it works. Now let me just submit it to prove it can pass for all testing cases. As you can see, it passed for all testing cases, and the time complexity is O(n) squared. And because we used the postorder.index, and this is O(n) time, and for the DFS, it is another O(n) time, so the time complexity is going to be O(n) squared. Because this n, preorder arrays.less, is a really small value, so that is why it is so fast. And also for the preorder array that are unique, and also for the postorder array, that is why we can solve the problem. Thank you for watching. See you next time.